below, its supremum should also be a member of R. So since now it is not bounded below anyway, so we can just look at the case of the supremum, because that is what exists in the set Z, the negative Z. And the second example there, you can check this from the notes, is that the set of rational numbers, we defined rational numbers. The set of rational numbers can be written in the form A over B, where B, the denominator, is not equal to 0, and the GCD of A and B, or the only common factor between A and B, is 1. So if you think of the set of rational numbers, all those numbers which can be written in form of a fraction, which means all whole numbers, fractions, and terminating decimals. Those ones belong to the class of rational numbers. But does that set obey the completeness axiom? Does it obey the completeness axiom? Like, does it have a supremum? Does it have a supremum? Does it have an infimum? Somebody was saying there's an echo from your side. The notes after sharing the notes after the lesson. Yeah, the notes were shared. I shared with your class rep. So check from your groups. I shared the notes much earlier. So maybe I don't know, echo could be because of my, I don't know, you can refresh your page if there's something that is not coming through for you. But I'm hoping that you can hear me now. So you are looking at the set of rationals. This set of rationals does not satisfy the completeness axiom, because you find that the set of rationals is an empty subset. The set of rationals is a subset of real numbers. Fine. Does it have its supremum in R? You see now for the set of rational numbers, since it's going from positive infinity to negative, from negative infinity to positive infinity, that's now the set Q of rationals. Then we can say that this set is, as a whole, is not bounded, because it doesn't have a supremum, because the supremum is infinity there. It doesn't have an infimum in R. So because of that, this set does not satisfy the completeness axiom. The infinity there is undefined, so it doesn't belong there. The two ends, or the infimum and the supremum, do not belong to R because they are undefined. So we have said that the set of rationals does not satisfy the completeness axiom. Another concept still on sets of rational numbers, sets of real numbers, is what we call the density of rational numbers. You will also find that in the notes that I shared, the density of rational numbers. Density of rational numbers. So what we mean by density here, just like as the name suggests, the density means now how packed or how dense is that set. So we can say, if we would say that the set is dense, if between any two numbers you will still find another one, a number lying between any two numbers. So we can say that between any two real numbers, there's a rational number between them. If you look at the real line, the number line, as we call it, if you look at the real line, like if you take some two numbers on the real line, like 1 and 2, between 1 and 2, you'll always find a rational number between them, like a half is there, a third is there. You'll always find a rational number between them. Even if it is between a half and a third, you will still find some rational number between those two fractions. So that brings now an aspect of the density of how are these numbers in this set packed or arranged. So we can say that for the density, we can say that between any two real numbers, there is a rational number. Between any two real numbers, there is a rational number. And this now implies that, therefore, we can say that the set Q of rational numbers, the set Q of rational numbers is said to be dense. It is a dense set because between any two real numbers, there is a rational number between them. So we can say that the set Q of rational numbers is dense in R. It is dense on the real line. It is dense in R. So then now we can state a theorem on the density of Q in R. The density of Q in R theorem. And this theorem is on density of Q, where Q is a set of rationals in R, and R is the set of real numbers. And the theorem states that if X and Y are real numbers with X less than Y, then there exists a rational number R such that this R will be in between X and Y, or will lie between X and Y. So this is a number that lies between X and Y. And remember we have said the density, a set is said to be dense if between any two real numbers there is a rational number between them. So the theorem just states or supports that property, that the set Q of rational numbers is dense in R. So it states that if X and Y, if X and Y are real numbers, with X less than Y, then there exists a real number, a rational number. Remember we are saying that the set of rationals is dense. there exists a rational number R such that R is greater than X but less than Y. It lies between X and Y. R is greater than X but less than Y. So in that case, that is what the density of Q in R states. And remember, we have just defined the density of the rational set of numbers. So after that theorem, we have an exercise there. If X and Y are real numbers with X less than Y, then there exists an irrational number W such that W is between X and Y. So remember the proofs for irrational numbers, what we said about them, we prove by contradiction. So the proof has been, that has been proved. So please follow through the proof from the notes. Follow the proof from the notes. It's using contradiction just the same way we used contradiction when we would discuss the rational and irrational numbers. So next we look at the structure, still on the structure of the real set of numbers. We now look at neighborhoods of elements in the set of real numbers. So when we have a subset of R, we would like to define neighborhood, or the neighborhood of members of that set. From the first principles, we define the neighborhood of points on the real line. So we can we shall define the neighborhood looking at the set of real numbers. You see now, for the set R of real numbers, subsets of that set could either be listed points, or they could be intervals whose endpoints are in R. So even if you consider a set with points 1, 2, 3, 4, then we can, in R, we can obtain a small open interval that contains a given point still in R. So we call such an interval a neighborhood of the given point. So anyway, let's first state what we mean by the neighborhood. So definition. A subset N of the real set R is said to be a neighborhood, is said to be a neighborhood of a real number P of a real number, say P, if there exists an open interval, say from A to B, such that this point P is the open interval from A to B, and this open interval is a proper subset of capital N, or rather that open interval is properly contained in N. So when this is the case, then we call N a neighborhood of the point P. We call N a neighborhood of a real number P because there exists an open interval which contains the point P, and this open interval is contained in capital N. So that is why I was saying that on the real line, we have points and intervals. So if I have a point A, and I can form an open interval that contains A, and this small open interval is contained in a bigger subset of R, or a bigger interval of R that we are calling capital N, then this capital N is referred to as a neighborhood of the point P. Is referred to as a neighborhood of P. For example, e.g., if we consider the set of real numbers, the set of real numbers is a neighborhood of each of its points. If you consider the whole of R, then since now the set R has many elements, each element, like we say 5, 6, 7, 8, 10, and so on, all those are members of R. They are real numbers, which means they belong to the set R. If I take a number like 5, I can obtain an open interval on that real line, maybe from 4.5 to 5.5, a small open interval containing 5, and this open interval is contained in R. So I have 5 is an element of the interval from 4.5 to 5.5, and this interval is contained in R. So in that case, we can say that we have that neighborhood. We can say that now R, which is the bigger set, is taking the place of our capital N. So R is a set. I have an element 5, which is contained in an open interval, and this open interval is a subset, or is properly contained in R. So an example, we can say that the set R, of real numbers is a neighborhood of each of its points. Is a neighborhood. Sometimes for neighborhood we write NBD, neighborhood of each of its points. It is a neighborhood of each of its points. But what about the set Q of rational numbers? The set Q of rational numbers, because we can find between some two rational numbers, we can find an irrational number. Going by the exercise I have left you to go through that proof. So between some two rational numbers, you'll always find an irrational number between them. So in that case, then the set Q of rational numbers is not a neighborhood of any of its points. This is because now the rational numbers are distributed on the real line, such that you may not find for every for every rational number an open interval that contains that rational number, because you can find an open interval that also contains some irrational numbers. So we are saying that the set R is a neighborhood of each of its points, but the set Q of irrational numbers, rational numbers, is not a neighborhood of any of its points. It's not a neighborhood of any of its points. So that's just an example and a counterexample of the neighborhood, that the set R is a neighborhood of all its points, but the set Q of rationals, because of existence of some irrational numbers, then Q does not qualify to be a neighborhood of its points. Another example, number 2. An open interval is a neighborhood of each of its points. If you consider an open interval, okay, let's state that first, that an open interval is a neighborhood of each of its points. So just the same way we have argued for the case of the set of real numbers, if I take an open interval from A to B, where A and B are real numbers, then for each element within that interval, I can always get a smaller interval containing that element, and that interval is properly contained in AB, in the bigger interval AB. So for each of these, we can do that. We can find a small interval which contains all the points in that interval, and that small interval being properly contained in the bigger interval AB. So that's why we are saying that an open interval is a neighborhood of its points. Another example is our special set, the empty set. So we can give that as an example, number 3, for the empty set. The empty set is a neighborhood of each of its points. So how would you explain that? The empty set does not have any points. So how is it that it is a neighborhood of each of its points? It is a neighborhood of each of its points. You see, to argue that, we can only say that there we have to be slightly technical and philosophical, that since the empty set has no elements, there is no member of that empty set which is not contained in that interval or in the set. So since there is no member, there's no element which does not belong there, then it's a trivial subset. Then the empty set is a neighborhood of each of its points. And after all, remember we always say every set is a subset of itself. So we shall now use that for the case of the empty set, that the empty set is a subset of itself. The empty set is also a subset of every other set. It's always a subset of every other set. So that's also an example a set, a neighborhood of a set. So the empty set is a neighborhood of each of its points. So there's no point of the empty set that does not belong to the empty set. The other definition, we can now give another definition of neighborhood. Another definition of the neighborhood. This time now, we call it the epsilon neighborhood. So, our definition, we want to define a neighborhood of a set with reference to epsilon. So, the epsilon neighborhood. The epsilon neighborhood. And this epsilon neighborhoods, we normally consider a point on the in the set R. A neighborhood will, when we consider a small positive, a small interval around a given point P in R, small positive change where epsilon takes such a small positive change, and this is applicable when the sets under consideration are in the Euclidean space. The Euclidean space here is the distance space. So if you are looking at sets now with reference to distances between points in that particular set, then moving, if you consider a small distance, which we are calling epsilon, greater than 0, a small distance around a given point P forms a neighborhood of that P, which is called the epsilon neighborhood, because it depends on that epsilon. Epsilon could be very small, it could be bigger, as long as it's greater than 0. So we shall say, we shall let P be a real number or belong to R, and let epsilon be greater than 0. Then we can say that an epsilon neighborhood of P is a set of the form, it is a set of the form capital N brackets P epsilon, which is equal to Y in R, such that the absolute distance between P and Y, P minus Y, the magnitude of P minus Y is less than that epsilon. So we are looking at this neighborhood with respect to P, and now our N, neighborhood N, relative to P, is defined by a small positive distance around P, whereby the distance from P to some real number Y, that absolute distance is less than epsilon. So we would describe N as an epsilon neighborhood of a point P, if that happens. Grammatically, we can look at it this way. If I were to represent this on the real line, I have my point P somewhere on the real line. Then, when I take a small positive distance from P on either side of P, I will have P plus epsilon to the right and P minus epsilon to the left. So that this open interval from P minus epsilon to P plus epsilon, it contains P. So it's a neighborhood of P. And this neighborhood is contained in R. So find this as an epsilon neighborhood because it's determined by a very small positive number that we call epsilon. This small positive number epsilon is called the radius of that neighborhood. It's like we are considering a circular ring around P of radius epsilon. That would give us a better definition of this epsilon neighborhood. So center P, radius epsilon, around it we have a neighborhood of P called the epsilon neighborhood. If you are looking at intervals on R, then it will just be an interval from P minus epsilon to P plus epsilon. If you're looking at distances on R2, that is a two-dimensional space, then you will be looking at epsilon as a radius with P at the center, and then you have a circular ring where epsilon is the radius, and so N P epsilon again defines a neighborhood of P, which is called the epsilon neighborhood. It's called epsilon neighborhood because it's determined by that small positive change. So you'll find that the epsilon there referred to as the radius of N, referred to as the radius of that neighborhood. There's an exercise there, an exercise on the notes that I would like you to go through. Given non-empty subsets A and B of R, let's see denote the set X plus Y such that X is in A and Y is in B. So we have that set. Show that A and B have a supremum, and then C has a supremum, and that supremum is equal to the supremum of A plus the supremum of B. So I would like you to just during your own time attempt those questions on the exercise that we have on the note, on the supremum and infimum of the sum of members of two sets. So that one will just be some additional work for you. Study the concepts of supremum that we have discussed, and try to show that if a set is the sum of two sets, then if A and B have supremum, then their sum also have a supremum, and that supremum is equal to the sum of the individual supremums of the two sets under consideration. So next we look at open sets. We are still studying sets of real numbers, their structure. We have looked at their neighborhoods. We have looked at boundedness of such sets when we define the boundedness, the upper bound, lower bound, supremum, infimum, maximum and minimal elements. We have looked at the neighborhoods of sets. So next we look at the terminology of some further terminology of sets of real numbers, and we want to study open sets. When do we say that a set is open. We have talked about open intervals and closed intervals. You know, intervals are subsets of the real line, subsets of R. But now we can have other sets which are not intervals, which maybe contain a listing of a collection of, just a collection of elements. So then I would like to define some terminology concerning sets as well. So open sets, what do we mean by an open set? What do we mean by an open set? So I hope someone will not confuse an open set for an open interval. Fine, an open interval, we looked at that on the as a subset of the real line. But now we'd like to use to define using some other terminologies, common terminology on sets. So the first terminology I would like us to define is what we mean by the interior. Before we define what open sets are, let's define the interior of a set, the interior point. Interior point of a set. You see, we have defined the neighborhood of the real line, or members of the real line, in two ways. We defined one using an interval, where we considered an interval containing a given point P, and that interval is contained in the set. So we would say that that set is indeed a neighborhood of P, because it's an open interval containing P, and that open interval is contained in the set. So we now want to define the interior point of a set. So let S be a subset of R. That is R for the real line. Then a point P in S is an interior point, of S if there exists, if I'll use the notation, if there exists an interval say from A to B, an interval AB, such that this point P is in the interval A to B, and this interval A to B is a proper subset of S, or is contained in S. So when we have this containment, like S now is a neighborhood of P, because if you look at the definition we gave for neighborhood, the neighborhood of P, then you can see S is actually fitting that description. So a point P in S is an interior point of S if there exists an interval AB such that P is in the interval and that interval is properly contained in S. So when that happens, then we say that P is an interior point of S. And you see, we can have several points which are qualify or which fit this description or this definition. So we can have several points which are interior points of S by the definition of an interior point. So then we can say that if you put together all those points which are interior points of S, then that set, the set of all interior points of S, is called the derived set, or rather is called the interior of that set. The set of all interior points of S is called the interior of S, or the interior of the set S. So it is a collection of all the interior points of that set. So the set of all interior points of S, denoted by S subscript naught, superscript naught, or just as we can write it as just int S, which is read as interior of S, then that forms the interior of that particular set. The collection or the set of all interior points of the set S is called the interior of the set S. For example, so if you relate this definition of an interior point, you can see it's borrowing from our definition of a neighborhood. You can see the containment there looks similar to the containment we used for neighborhoods. So for example, e.g. 1, if we take S to be, if S is the set, then a closed interval, say from 2 to 4. S is a closed interval from 2 to 4. Then what will be the interior of this set? You need to look at how this set appears on the real line. It's closed from 2 to 4. And if you want to find all the interior points, every point in between 2 and 4 there qualifies as an interior point, going by the definition, because you can always find an open interval containing that point, and that open interval is properly contained in S. So all you need to do is, like for example, now take the endpoints. Are the endpoints interior points of this set? If I consider 4 on my real line there, am I able to get an open interval containing 4, which is properly contained in S? You see, if I take a subset like 3, 4, an open interval 3, 4, this open interval 3, 4 is a subset. Is a subset of the interval 2 to 4, the closed interval 2 to 4. And does this open interval containing P, is it properly contained in S? So at the point 4, 4 itself, the endpoint at 4, if I take a small open interval containing 4, then it will not be properly contained in S, because I have a small half side of my open interval which is outside the S. So it fails to be a proper subset of S. Likewise for 2. If I take 2 and I take a small interval around 2, part of this, my open interval containing 2, will be outside S. So it will not be contained in S, right? So we can say that all the interior points of S, or all the interior points of S, 2 and 4 fail to be interior points, or they fail the definition of an interior point. And therefore we can say that for if S is a closed interval 2 to 4, then we can say that interior of S, so S naught, S superscript naught, will be an open interval 2 to 4. So the interior there is open. It's an open interval from 2 to 4, because only the two endpoints 2 and 4 have failed to be interior points. So basically, that's an example. It's an example of the interior. Sorry. It's an example of the interior of the set S, where S is defined as a closed interval. So you only check if each of the points of S satisfy the definition of an interior point. Another example, if S is an open interval from 2 to 4, if you take S to be, and this time not closed, but an open interval. Don't know what is happening to my throat. So S is a closed, an open interval. We want to investigate, or want to find the interior of this set S. Looking at, if you were to represent this interval on the real line, let me just squeeze my diagram on the side. The interval will look like this, from 2 to 4. But being an open interval means that the endpoints 2 and 4 do not belong to the set S. So I'm interested in the interior of this set. If I take any points inside, any points within the boundaries of this open interval, I can always find an interval containing each of them properly contained in the set S. Now investigate the endpoints. The endpoints at 2 and 4, remember, being open, it doesn't include 2 and it doesn't include 4. Or rather, the endpoints 2 and 4 do not belong to the set. So what will be our interior? The interior of S will be every point in there, in that interval, apart from 2 and 4, or apart from the 2 endpoints. So the interior of S will be again an open interval from 2 to 4. You see, being open, it doesn't include the endpoints 2 and 4. So in this case, we can see the set S and the interior of S are equal. But when it was a closed interval, the interior of S was an open interval. So the two sets were not equal. The two sets were not equal. So we have defined the interior of a set and also illustrated with some example. You can look for some other illustrations of the interior of a set. And then at this point now we can define an open set. When do we say that a subset of R, remember it is real analysis, so we are dealing with entirely, we are studying sets of real numbers. So when do we say that a set of real numbers is open? So at this point we can define an open set. Definition, open set. We can say that a subset S, a subset S of R, where R is a real line, is said to be open is said to be open if every point of S is an interior point, of S. If every point of S is an interior point of S, then we say that S is an open set. That is, S is open if and only if the interior of S, so S with a superscript naught, is equal to S itself. If the interior of S is equal to S, then we say that S is an open set. In the two examples I've given, the first example where S was a closed interval, its interior was an open interval, so S is not equal to S interior. In the second example where I gave S as an open interval 2 to 4, its interior was also an open interval 2 to 4. So there, the S interior is equal to S, or the interior of S is equal to S. So in the example we have, the two examples we have given, we can say that the second one, where S is an open interval from 2 to 4, is an open set. E.g., if S is this open interval from 2 to 4, then S interior is also an open interval from 2 to 4, and therefore S interior is equal to S. And so you can conclude and say that therefore S is open. S is an open set. The S we have illustrated in the second example above, S there is an open set. The reason is the set is equal to its interior. Every point of S is an interior point of S, so it is an open set. Some examples. Example. Number 1, since we are now looking at sets or subsets of R, or sets in R, then we can say that from our illustration up there, every open interval is an open set. That's a general example we can give. We can say that every open interval is an open set. This is because when you are given an open interval, when you obtain its interior set, it will still be that open interval. So both the interior set and the set itself are equal, so it is open. Another example, I want to give an example which is not open. A closed interval, this now agrees with our first example above. We can say that a closed interval is not an open set. A closed interval is not an open set. So remember now, when we talk of an open set, when I give this question, either in the exam or even in a CAT, people try to say, oh, an open interval or an open set has no boundaries. You see now, in real analysis, you don't just use words, because you will use one word and it means something else. So please take very keen interest in the terminology and the language that is used. Some of you will say an open set has no boundaries, and yet we have a whole different definition of a boundary. So because I will use that definition strictly, when you use boundaries in open sets or closed sets, then the meaning of a boundary there may be different from what you mean or what you think as a lay person. So take keen interest in the language that is used. So an open set is open if, or rather a set is open if it contains all its interior points. There's nothing to do with its boundaries, having boundaries or no boundaries, because now boundaries is a completely different terminology. If we have not defined it, we will define it later. So a closed interval is not an open set. Number 3, another example. The empty set is open. The empty set is open. This is because this is another one where you just argue it just theoretically, because now looking at our definition of an open set, we have said that a set is open if every point of S is an interior point of S. When the set is empty, there is no point of that empty set which is not an interior point. So it is an open set. So we are saying that the empty set is open since there is no point, of the empty set which is not an interior point, So in that case, then that's why we are saying that the empty set is an open set. It contains all its interior points. There is no point in the empty set that is not an interior point. Another example, number 4. Is that we have the sets of natural numbers, the set of integers, the set of rational numbers are not open sets. So the sets n, I'll just use the notation, n for natural numbers, z for integers, and q for rational numbers. So the sets n, z, and q are not open sets. If, for example, I can illustrate with a set of natural numbers, the counting numbers, which is 1, 2, 3, 4, and so on. Now, you see, for this set to be an open set, each of its points must be an interior point. So I should find an interval containing 1 which is properly contained in N. But you see, I have an interval from 1/2 to 3/2 to 1.5. This interval contains 1, fine. But this interval is not a member of N, because fractions, you see, natural numbers are whole numbers. They are whole numbers. So I do not have a situation where I have 1 being a member of this open interval, and this open interval is properly contained in N. See, the interval of 1/2 to 3/2 does not contain only natural numbers, so it's not properly contained there. So because of that, the set N of natural numbers fails to be, or fails to contain its interior points. The same will apply to Z, because Z are whole numbers. Whole numbers, both negative and positive, including 0. So again, if you take small intervals around the members of Z, you will have some intervals, the interval will contain some members which are not in Z, which are not whole numbers in Z. So again, that fails. And the same will apply to R, to Q, for the set of rational numbers. So we are saying that these 3 sets are not open sets. They are not satisfying the definition of open sets. Another example we can give, number 5. You have all these notes, I shared them earlier, so we are just discussing. Number 5 is that if now you consider R, the set R of real numbers, I hope you know the difference between all these sets. Like between Z and R, you see R comprises of all numbers that can be represented on the number line. All real numbers, be they whole numbers, be they negative, positive, even 0 included, whether they are fractions or decimals, as long as they can be represented on the number line, then those are real numbers, even if they are surds. You see, surds are not rational, but they are real numbers. All the numbers that can be represented on the number line belong to the set of real numbers. So for number 5, we are saying that the set R of real numbers is open. This is because now it actually fits the definition of an open set. There's no every real number, we can find an open interval containing that real number, and that real number, that interval will be properly contained in R. So the set R is open anyway. We even stated earlier that the set R contains all its interior points. So those are some examples of sets that are open, and also some examples of sets that are not open. The next one, it's a theorem that I would like us to prove. I think that this will be the last item we are discussing for today. Then we call it a day. So we will state a theorem concerning now open sets. Theorem. This theorem, we will state it in 2 parts. Part 1 of the theorem, or number 1, states that the union of an arbitrary collection of open sets is an open set. the union of an arbitrary collection of open sets is an open set. And the second part of this theorem is the intersection. When we take the intersection of a finite collection, for intersections we take finite collection because if it is infinite, you can carry out the intersections until you are left with an empty set. Because intersections go shrinking, since you are only considering those elements that are common to the sets in question. So the intersection must be finite. You can't just intersect on and on and on infinitely. So the intersection of a finite collection of open sets is open. The intersection of a finite collection of open sets is open. So we shall prove these two and then we call it a day. We look at the proof, the first part. To prove part one, we are looking at the union. So let you remember the definition. That's why we started the course by reviewing a bit of set theory. So let U be the union of a collection of open sets. Let U be the union of a collection of open sets. That is, U is the union for alpha over some interval of A alphas, where each A alpha is open, where each A alpha is open for each alpha is open for each alpha. Then we can say that if this union is empty, if U is an empty set, then we have said the empty set is open, then U is open. If U is not an empty set, and we see now if it's not empty, it means there's some element in it, and we let X belong to U or be an element of U, then X belongs to A alpha for some alpha. You see now being the union, it's a collection of all that. So if X belongs to that union, it must belong to a certain A alpha. So for some alpha in the interval under consideration I. And now since A alpha is open, since this A alpha is open, there exists an open interval. From definition now, there exists an open interval. There exists an open interval AAB such that X will be contained in that open interval, and that open interval will be properly contained in A alpha, such that X belongs to AB and AB is contained in A alpha, is properly contained in A alpha. But we are saying that but A alpha is contained in the union, but A alpha is contained in U. You see now U is the union of all the A alphas, so A alpha belongs to U. Then what this implies is that we have this containment. X is an element of some interval AB. The open interval AB is properly contained in U, and this U is the union, U is the union of all the A alphas for alpha in the interval I. So because of this containment, then we are saying that this union of open sets is also open. So we can conclude here and say that therefore U is a neighborhood. U is a neighborhood of X, and X belongs, and X, since X was arbitrary, so X being arbitrary, implies that U is open. It implies that U is open, and so that now ends our proof that the union of open sets is an open set. So for number 2, we now prove that the intersection of a finite collection of open sets is also an open set. And the argument will just be similar, only that now intersection and unions, of course, are different. So the structure of those two sets is different. So we shall let AI, for I from 1 up to n, we have this collection. Let this be a finite collection. Be a finite collection of open sets. We want to show that, let's say B, where B is the intersection for I is equal to 1 up to n of AI, is open. Now suppose B, this intersection, suppose B is not empty, is not an empty set. If not an empty set, it means there's some element, it contains some elements. Suppose B is not, and we let X be a member of that B, that set B. Then X, you see now by the definition of intersection, the elements of the intersection will be common to all the sets under consideration. So if X belongs to this intersection B, then X belongs to AI for every I, because it's now common to all the open sets AI are involved in the intersection, where I, for all I from 1 to all the way up to N. But now, since AI is open, you see now, since the AI is open, by definition, it satisfies the condition for an open set. So since AI is open, there exists an open interval. Now from definition, an open interval AB such that X belongs to this open interval from A to B, and this open interval is properly contained in AI for every I. And since now we are looking at the intersection and B is that intersection, then we can say that therefore X is contained in the open interval from A to B, and this open interval is properly contained in the intersection of AI for I from 1 up to N, and this whole intersection is the one we called B. So you can see the containment. X is contained in the interval AB, and this interval AB is properly contained in B. So we can say here, hence B is open. It meets the requirements for the definition of an open set. I want to make a remark and stop there, so that now our next class we will start by proving that remark or illustrating that remark. We want to make a remark that we have said that the intersection of an arbitrarily, the intersection of a finite collection of open sets is open. So the remark we want to make is that when you are considering the intersections, if you consider now if you consider open sets and you are looking at the intersection, if this intersection is not finite, then you may not necessarily end up with an open set. If the intersection of this collection of open sets is not finite, then that intersection is not necessarily open, as we shall illustrate in the next class. So I think we can state the remark then and be able to illustrate it. But for now, let's stop at the definitions, at the proof of these two theorems, and then we make the remark and be able to illustrate and prove the remark in the next class. So we shall stop there. I have shared, some of you are asking if we will get